Hi everyone. So now we have a question where we have a projectile that is thrown out horizontally, right, purely horizontally on a slope, and when it hits the slope again, right, it makes an angle alpha with the slope, and we're interested in asking, right, how if I vary this initial horizontal velocity, how does it affect the angle alpha? And this is a good question because this question is a prime example of certain type of reasoning where you need to say, oh, if this quantity increases, then another quantity increases linearly, another quantity increases quadratically, and hence the ratio increases linearly or something like that, right? And this type of reasoning is common in SJPO questions, and so this is the first question where we'll encounter such reasoning. And it'll make more sense if I go into the details, which we are going into now. So yeah, so first of all, let's observe that if instead of asking, right, when the ball hits at an angle alpha, right, instead of asking what the angle alpha is, right, we actually it suffices to ask what is the ratio of the x and y components of the velocity when it hits. And the reason is because if we draw it out vertically, draw the vertical and the horizontal, this angle is theta by alternate angles, right? And ball hits like coming here, and this angle over here is pi over 2 minus alpha minus theta, right? Because this is 90 degrees. And so if the velocity is this arrow over here, then taking the horizontal component vx and the vertical component vy of this velocity v would help us determine the angle alpha by the following relation. Right, so tangent of this angle over here is equals to the opposite over the adjacent. So it's equals to Vx over Vy. Okay, that's great, but there's something I would like to emphasize over here, which is that Vx over Vy, velocities are functions of time, right? So if we write Vx, it may be a bit ambiguous, right? It may be a bit ambiguous that, oh, which velocity are we referring to at what point in time? So just to be extra specific, right, I'm going to put velocity as a function of time at the time value where t hit, right? T hit meaning the time that it takes, time that it hits the slope again, right? Over t vy t hit. So velocity vx and vy, they are functions of time, right? So I'm asking about the ratio of the velocities at the time t hit when the ball hits the slope again. Okay, so that's just to be extra pedantic. And what do we see over here? We see that instead of the question asks us to reason about alpha, right? But alpha is this opaque quantity over here, which is quite hard to talk about. So instead of that, we have reframed the question of how alpha changes into a question of how the ratio of the velocities change, right? And this question of how the ratio of the velocity change is much more accessible because velocities appear in the equation of kinematics. Right? So we've changed our focus from calculating alpha to calculating the ratio of the velocities. And to be specific, right, we're not just asking how the velocities individually change, right? Of course, if we increase the horizontal velocity over here, then if we increase the horizontal velocity, right, from v1 from v2 to v1, right, then of course the individual velocities vx and vy, right, when it hits the slope again, is going to increase, right? Each of them is going to increase. But the question over here is that we're asking how both of them increase, right? Whether it's quadratic or linear or whatever else, whatever other kind of dependence, we're asking how they change, and specifically we're only interested in the ratio, right, of vx over vy. Okay, so this ratio aspect will be emphasized later because we see that there'll be a certain reasoning that will tell us how the ratio changes, and basically we do not need to find we are more interested in the ratio than the individual velocities. So yeah, okay, so I'll go if I want to be extra specific. Vx is a function of t hit, right, the time that it takes to hit, and vy is a function of the time it takes to hit, right? And these two quantities, right, this t hit, the time that it takes to go from being thrown to hitting the slope again, right, this is a quantity that depends on the initial velocity that you throw it out at, right, vx 0, vx at time t goes to 0. And t hit, right, here is a function of vx naught also. In other words, right, we're interested in finding how this quantity vx of t hit of vx naught over vy of t hit of vx naught changes with respect to vx naught. Okay, so the dependence is as follows: vx depends on this, which depends on this. And if I want to be really mathematically rigorous, I'm interested in finding the derivative of this function with respect to vx naught. But that's that's just being extra mathematically rigorous. So I'm interested in finding the derivative. And so how are we going to approach this, right? If we want to find how vy, depends on vx naught, right, it suffices, right? If we want to find how vy depends on vx naught, it suffices to find out how vy depends on t hit, right, and how t hit depends on vx naught. And if we know how both of these dependents work, we can compose the dependence such that we find how varying vx naught affects vy through t hit. If I want to be really mathematically rigorous, this is just the chain rule, right? If I differentiate with respect to this parameter, right, then this is equals to dvy over dt hit, right? How vy, there's this dependence over here, so this dependence over here multiplied by dt hit over dvx naught, right, which is this dependence over here, right? This is the multivariate chain rule. Sorry, it's not multivariate chain rule, it's just the single variable chain rule for differentiation. Yeah, but that's just the chain rule isn't really necessary over here, because it turns out the dependence is actually linear, so it's quite simple. So, but I want to find how, in order to find how this ratio changes, I need to find how the numerator and denominator changes. And in order to find how the numerator and denominator changes, I need to find how each of the individual component velocity functions change with respect to t hit, and how t hit changes with respect to vx naught. Okay, so for the first part over here, how does vx vary with respect to vx naught? Okay, let's do something a bit simpler first. How does t hit, right? How does the time of flight, how does the duration of flight vary with respect to the initial velocity? It turns out that the time of flight varies with respect to the initial velocity in a simple way, right? One can see that because the vertical acceleration over here is g, right? If we had thrown the ball with a higher velocity, then all that happens, right? All that happens is that the ball will go like this, and it will perhaps go here. And because the acceleration is g in both cases, if we take snapshots in time, so imagine two people throwing two balls, right? One at a lower velocity horizontally and one at a higher velocity horizontally. And then we take snapshots of time, right? For each time, we take a photo. So maybe at this point in time, it looks like this. And at this point in time, it looks like this, right? And you see that if we take a snapshot, we take a photo, these two balls were thrown at the same time, just with different velocities. But because vertical acceleration is the same, right, it's g downwards, at the same time, right, when you take the photo, they are at the same height, right? Only the horizontal component of velocity changed, right? However, we see that when we take a snapshot such that the first ball has hit the ground, the second ball is still in the air, because of the fact that it had a larger horizontal velocity, which gave it a larger horizontal distance, right? Give it a larger horizontal distance, right? And because of this horizontal distance, even though it's at the same height as the ball that was thrown slower, it has traveled further and there's more distance for it to fall. So hence, we can deduce that as Vx naught increases, right, T hit also increases, right? That's a very intuitive reasoning. How exactly it changes, we currently do not know, right? But at least we know that increasing the initial velocity will increase the time it takes to hit the ground. Okay, so that's a simple observation, right? I just wanted to warm you guys up to the so this dependence qualitatively is very obvious. Okay, how does Vx vary respect to Vx naught, right? Vx, we can see that Vx, right, there's no horizontal acceleration. So Vx as a function of time is actually just constant and it's just equals to the initial velocity. So in other words, Vx doesn't depend on time, right? Derivative of Vx with respect to time is 0. But Vx, if it is equal to the initial velocity because there is no horizontal acceleration. So this is the dependence of Vx at the time of hitting. At the time of hitting, this dependence of Vx at the time of hitting with respect to the initial velocity. So we can see that as the initial velocity increases, right, the velocity when it hits increases linearly with respect to the initial velocity. Okay, so this is our first dependence. This is how our numerator over here depends on Vx naught. Now, how does our denominator depend on Vx naught? Our denominator, Vy of T hit of Vx naught, how does this quantity change? To do so, we actually need to find out precisely, to do so, we first observe that if I set coordinates such that this is at the origin and x is rightward positive and y is downward positive, then Vy is simply g times T hit. Okay, so this is how Vy depends on T hit. So if I want to be extra specific, this is how Vy depends on T hit. Now, we know that T hit increases as Vx naught increases, right? We reasoned it out over here. We know that T increases as Vx naught increases. But how exactly? That's what we're going to find out now. Right, so we're interested in the dependence of T hit on Vx naught because we already have the dependence of Vy on T hit. So we already have this connection. What's left is to find this connection precisely, numerically, right? Analytically, I mean, when you find a mathematical instead of just when you find a quantitative correspondence, right? Quantitative relation instead of just a qualitative relation. So to do so, we need to find when the ball hits the ground. When the ball hits the slope. And to find this time, we need the positions as a function of time. So notice that y as a function of time is just half gt squared, right? And x as a function of time is just the horizontal velocity, which is constant, right? So it's just the initial velocity times time. And the moment that the ball hits the slope, at that very moment, right, at that point in time, the coordinates of the ball is y of t hit and x of t hit, right? And specifically the ratio of the y coordinate and the x coordinate, right, is tangent theta. Okay. So with this relation, if we substitute these functions, right, into this relation, what we get is an equation actually relating t hat and vx naught. So let's see that. Let's work that out. So half g t hat squared over vx naught t hat equals to tangent of theta, and that gives us t hat equals to vx naught tangent of theta times 2 over g. Okay, so we see that t hat as a function, of vx naught, right, is linear, right? This curly sign means proportional. So we see that previously we qualitatively understood that as vx naught increases, right, it makes sense that the time of flight is greater because you're throwing it further horizontally. It's more time, it's more time to spend in the air, right? But now we have derived a precise relation of how the time of flight depends on the horizontal velocity, and we know that it's linear because the rest of the quantities over here are just constants. Okay, so t hat is linear with respect to vx naught, and we know that vy is linear with respect to t hat. So that tells us that vy is linear with respect to vx naught. Okay, so vy varies linear with respect to vx naught, and all that's left to do is to look at the ratio of vx over vy. So we showed here that vx, right, because there's no horizontal acceleration, vx as a function of time is just the initial velocity. So vx is proportional to vx naught. Right, vx at the hitting time is proportional to vx naught. And we also showed that vy as a function of time is proportional to vx naught. So vx as a function of time, vx as a function of vx of t hat is proportional to vx naught, vy of t hat is proportional to vx naught. So because both of them are linear, you take the ratio, it'd be constant. So in other words, the ratio, these two imply that vx over vy, right, is proportional to 1, right? It's proportional to it's constant. And hence, the ratio of vx over vy, right, at the time when it hits the slope is constant with respect to vx naught, the horizontal velocity. And because vx over vy is constant with respect to the horizontal velocity, right, because this ratio is constant, we have shown that this is constant with respect to the initial velocity, the ratio here alpha is also constant. So no matter what velocity you throw it at, right, the angles will always be the same, and hence the answer is A. Okay, so to recap what we did, right, it was quite a lengthy procedure. We first said that, hey, instead of finding the angle alpha, we just need to find the ratio of the components of the velocity, vx over vy, at the time t hat. Okay, and this t hat itself is the time of flight, right? Because it is the time of flight. This t hat is the time of flight, and this t hat depends on vx naught. So we're looking at a chain of dependence, right? Vx, right? The velocity at which it hits the ground, hits the slope, right? The horizontal component of the velocity and the vertical component of velocity when it hits the ground depends on the time of flight, which depends on the initial velocity. The Vy dependence was obvious, right? The Vy dependence was obvious because the longer you the Vy is just linear with respect to t hat, right? Because because the longer you fly, right, the more you get accelerated, right? Because Vy is just g t hat. But we didn't know what this t hat t hit depended on the initial velocity. What we did was that we found the ratio of the displacements, and using this relation, right, using the fact that when the ball hits the slope, the positions must be related by the ratio of the displacements must be tangent theta. Using that fact, we deduced that t hit is linear with respect to Vx naught. And hence, from there, right, we know that Vy increases linearly with respect to Vx naught, the initial horizontal velocity. Then it was then obvious that Vx, right, is in fact equals to Vx naught. The horizontal velocity doesn't change. And hence, the ratio of Vx over Vy remains constant with respect to Vx naught. Okay, so no matter what value of Vx naught you choose, right, the ratio of Vx over Vy is always going to remain constant, and hence the angle alpha doesn't change. Okay, so I hope that this kind of reasoning, right, it takes a while to navigate this kind of reasoning. I recommend you be able to do it yourself as well. But this kind of chain of reasoning, where this depends on that depends on that, and that depends on that, this chain of reasoning is quite common in SJPO, especially the MCQ questions. So yeah, so I hope that you get more practice with this, and this is just the first example where we see this kind of chain of reasoning happen. Okay, so if not, I'll see you in the next question.